So in looking at the second law of thermodynamics, we are looking at a baseball that is in flight. It has left our hands. It is slowing down due to the drag force. Now what we want to do is we want to take a closer look at what is happening in the fluid behind the baseball. So we're looking at the fluid in the wake of the baseball. And what we know is that the fluid has random velocity fluctuations. So this is our baseball. It has gone off. Now what we're going to do is we're going to look at a section of fluid that is in the wake of that baseball. So it's behind. And we'll now make a new system, and that system will encapsulate the fluid. And given that we have random velocity fluctuations, if we were to put a hot wire probe or laser Doppler velocimetry or particle image velocimetry systems for measuring velocity, we would learn that the velocity here is changing as a function of position, 3 dimensions, as well as time. So it's a non-steady and actually a non-stationary flow. It's what we call decaying turbulence. And so what we're going to do is take a look at the energy equation for an incompressible stationary fluid. So this would be from a course in fluid mechanics. And we're just going to look at it so that we can examine the terms that are in this equation. And when we say it's a stationary fluid in this sense, that means that it's not moving. It has no net convective velocity. So looking at the energy equation, we would result with an equation that looks like this. The first term here, this is the change in internal energy of the fluid. So it's basically the specific heat times the density times the change in temperature with time. One thing to note though, there are no velocity terms. The second term that we have here, this is thermal conduction. If you remember a couple of classes ago we talked about forms of heat transfer. We had Fourier's law there. This is a similar representation, although it's from the heat diffusion equation, but it would represent thermal conduction within the fluid. And the thing to note there, again, there are no velocity terms. So velocity does not appear anywhere in either the first or the second term. The only place where velocity will come in is this last term that we have here, and that is referred to as being viscous dissipation. And what it is a generation term. So that means that velocity, shear within the velocity, is generating thermal energy. So I'm not going to write that term out. However, if you did expand it, you would see there's a lot of velocity terms in it. It's a partial differential. So essentially what we have is this dissipation term times the volume of our system is proportional to the drag times the velocity. which we said was equivalent to the work being done on the ball, and in this case it's the work being done on the fluid. So that is a way of looking at that. What we're going to do now, we're going to go from fluid mechanics and look at an equation that you may see in a course in heat transfer. So the above equation looks a little bit like the heat diffusion equation that you would see in the first few pages of any textbook in heat transfer that a mechanical engineer would use. And we call that the heat diffusion equation. Again, it's a partial differential equation. This is the Laplacian of the temperature field, plus then a heat generation term, which is the last one. So what that shows, that this first term is very similar to the first term that we had in our energy equation. The second term was the thermal conduction term. I've taken the K, the thermal conductivity, and divided on the other side. And then the last term, that is our generation term. So this here is equivalent to the term that we had earlier. It's proportional to the viscous dissipation term. So what that tells us so the drag force from the baseball going through the fluid causes the fluid to churn, and this contributes to the viscous dissipation, which is basically a term that represents the conversion of velocity fluctuations into thermal energy. And so where does that work go ultimately? It goes into random velocity fluctuations, which then through the viscous dissipation term are converted into velocity shear and thermal energy. And once it goes into thermal energy, it raises the temperature of the fluid. So that's interesting. It tells us that by raising, when the ball goes through, the fluid temperature behind the ball goes up. So by this logic, what I can assume, because I have the first law that tells me that there's heat, there's work, internal energy, kinetic energy, potential energy, that's what we've used where we started. But by this logic, we can say that heating the fluid behind the ball so if we have a ball that's in flight moving along and somehow we are able to transfer heat into the fluid here, if we do this and we do it well, we should be able to make the ball go faster. Now, we all know that that won't happen, And the reason is because energy flow does not always go the way that we want it to go. The first law, when you look at the first law, it would tell us that this logic would be perfect and would make perfect sense. However, in reality, that is not the way that nature works. So what we can say is that an increase in the random kinetic energy of a system does not ensure that work will be done. So looking back at the first law, we had Q minus W equals delta U plus delta PE plus delta KE. What this tells us is that direction of flow, or of energy flow, I'll call it energy transfer, is not determined by the equation. And this is an important, although somewhat subtle point. We can use the first law, but it is the second law that enables us to figure out which way the process will go. And so that's what we will now venture into, is taking a closer look at the second law.